Hello everyone. I think it's time is 2:40 right now. So here I am. So I'm here to talk about TSO to VPN. So um, let's start by introducing who I am. I'm Samuel. I'm from ExpressVPN. I'm a junior infrastructure developer, and I'm in core VPN and both core VPN and trusted server team. So you can see me like a mixed bag of low-level networking and server management stuff. So I make a lot of things happen, good or bad. So the plan for today is hopefully to cover what is TSO, what is GSO. So why should we even begin to care about something that is traditionally handled in hardware, and why there is benefits in doing packets in the software way. So after that, I'm also going to tell you how to put GSO in our existing VPN. And hopefully we can wrap this up in 30 minutes or so. So this talk will focus on primarily Lightway, our VPN protocol. So unlike WireGuard, we have infrastructure needs. We have millions of users, and we absolutely do not want to manage millions of public-private key pairs. We also designed the Lightway so that it has a very flexible ingress, egress plugins. So that is what makes it special in the first place. So that means we can freely inject and put secret source and experiment with the protocol as flexible as we needed to. And we also make it so that the authentication is pluggable. And unlike WireGuard, it's very pronounced in the subjectivity. So we rely on TTLS for encryption, but the authentication is interchangeable, so you can free to mess around with it. And there's a QR code to the GitHub link, but without further ado, we can take a look into how Lightway works from the client part. So this is very simple. Virtually every VPN does this. OpenVPN, WireGuard, stuff. So basically how it works is that your app, whatever you're using, you're browsing YouTube, you're watching Netflix, your data will be crossing into the kernel boundaries, passing through the TCP IP stack, usually. And if you install our ExpressVPN app or set up some other VPN routing, it will be redirected to a TUN device. We'll circle back what is a TUN device, but it's sort of like a virtual network card interface that makes it easier so that we can take your traffic without really reinventing the whole wheel of a network card. But it will read into Lightway. So Lightway will encrypt your packets and then go back to the kernel space. Because we prefer to do Lightway in user space, so that's what we did. And in the end, the traffic will route out to the network interface. But while this might seem simple, the underlying cost we pay for it is quite severe. Because every time you've crossed the user space and kernel space boundary, you exact a really heavy cost of at least a copy and allocation, to say the least. So when the app is crossing through the kernel boundary, it's already kicking a copy tax. So what is a copy tax? It means that the kernel cannot trust whatever you put into it. So it has to at least to copy it once to kernel space and verify that everything is right before accepting the payload as is. And this happens is complicated for Lightway because it has to take things into the user space and then back out to the kernel space again. And that is before even talking about we have to use the SSL library, and that exacts a copy as well. So it's just performance gone, just crossing the boundary. Some people may say, hey, it's just like a packet is a maximum 1,500 bytes. It can't be that bad, right? But consider this, if you are doing it on a server size scale, like 10 gigabytes per second, you are actually doing like crazy number of bytes per second. And that is like 800 kilo packets a second. And that will be 4 million copies just by the previous graph. And that is before even calculating all the things that account for interrupts, page faults, zero pages, wherever. So the CPU, you're essentially wasting a considerable portion of CPU cycles just on copying this. So how does this work in the end? Because right now you see we have like 10 gigabits home networks now. So our routers cannot be handling all that traffic, right? So I did some statistics on the Lightway binary. We will get back to that later. So what the VPN is actually doing is that there is a frame graph, by the way, so we are clear. So this is how you actually measure what the program is doing inside measured run, like let's say 60 seconds. And you can see where the program spans cycles on in each core in the stack. So where did my cycles go? Turns out the Lightway binary is spending, if optimizations are off, is spending around 16% of the CPU cycles just on crossing the boundary and managing memory, stuff like that. Like people would think that for a very simple VPN protocol, the main thing it should be doing is encrypting and decrypting stuff. That's the most basic thing we can think of. But no, it only accounts for 70%, which is really crazy to think about for me, at least. So there must be a way to mitigate all this. If our routers are working, our routers are not supercomputers. They cannot handle this much traffic. So what the hell is happening? So if we look over to the hardware side of things, so the hardware people actually figured out a way before us 20 years ago. That is called TCP Segmentation Offload. And what it does, we'll get to it in next slide. But essentially what it does is that the hardware of the network card will support various functions like checksum offload for IP and both IP and TCP UDP. And it also does the segmentation for you in the hardware. So that's why it's so fast, because the CPU doesn't handle it ultimately. You just pass it along to network cards and let that pick it up. So this design originally was invented, I'm not sure what now, because the different vendors have different implementation for stuff, but at least this one is from Intel, the driver design. And then the kernel actually doesn't have that design at that moment, but kernel looks at all the different vendors and then they all have this similarity, and then they just decided to generalize it into TSO. So how TSO works is that basically, instead of, because all the packets that can be passed through the internet is only 1,500 bytes, right? So if we can't get that, if we don't do that, what can we do to mitigate all this traffic, all these packets? So what we do is we pack all the segments into a super packet, and we only segment them in the hardware. So the software will only see 64 kilobytes at once. And then the hardware will take care of the rest. And this is really efficient because the CPU doesn't have to handle each packet. They can just pass it along to hardware. So in practice, what we will do is we set up a partial header of IP and TCP. And then for each packet about to pass on to the wire, we complete the header and checksum for each payload or segment. So, and then we can send that to the wire. And by default, the hardware will do this. But wait, we are a software binary. we don't have silicon to do all this checksum offload or segmentation for us. We have to implement all that ourselves. So that doesn't really translate to us. We can't make use of this. So something magical happened. So Herbert at NetDev mailing list in June 2006 pointed out that most of the savings in TSO actually come from traversing the network stack once rather than many times. Those savings can be obtained without hardware support. Let that sink in for a moment. So you are telling me this, even without the hardware, that I can segment all the packets in software and keep the benefits, and then the segmentation, hardware segmentation part is just a cherry on top kind of thing? Wait, this sounds like a great use for a VPN. Like this, the cake we are going for, and we can actually do this and still pull a W on this. So this is basically what GSO does. So instead of letting hardware to do the TSO bits and stuff, we recognize that there are overhead to be saved, even if the hardware doesn't ultimately have TSO. So we just, if it doesn't have TSO, we just segment it in software, and we will still keep like 70, 80% of the benefits. So who cares about TSO, right? So that is what GSO is. And other than TCP, it also works for UDP, which is awesome. So there is GRO. It's the reverse of GSO. So packets come in, and then you combine them into a super packet, and then send them through the kernel stack once, instead of like 45 segments. It's symmetrical. It's like reversible, so it's pretty clean. They tried to do that in hardware, but it broke, unfortunately, so it's dead. But okay, what about us? So circling back, we got GSO, we got GRO. We don't really have TSO, but we can pretend that we have. We are in user space. So the rest of the talk is solely dedicated to how we are going to still pack that magic saving of per packet overhead. So the first step is that we actually need to tell the kernel that we, as a user space driver, faking network card, we actually accept parcel checksum and all that goodie, so we can take kernel's work and then speed it up, basically. So the most important fields here are the GSO size, which dictate the MTU size, basically. So around 1,500 for maximum. And the checksum offload, so csum start is basically where you should be checking the checksum. And then the offset is where you should be writing that checksum in. But that is too complicated. And unfortunately, this is even more complicated. This is how I actually designed the GSO pipeline in Lightway. So like I said, we take in a header that tells kernel that we accept all these checksum offload, and then we complete it for each segment in the TCP super packet segments. And then we do the core encryption part that people know mostly about. And then after encrypted, the packets are encrypted, we just collect all of them and then wrap it in a I/O fig. And then we pass it along to the network card. So what is I/O fig? I/O fig is basically a way to do scatter, gather I/O in the kernel. So kernel actually enables you to just read this part of memory, and then read that part of memory, and then read another part of memory, and then combine it all together without you doing the copy yourself. So this is actually quite useful because like the usage I talked about, you can also do alias. So you can reuse the same, for example, header or any other payload that you want. And then you just copy it multiple times. You don't actually have to do any copy. And copies are expensive. So this is very good to get into. And then we get, the concepts are simple, but the execution is very brutal. I would say that I spent a lot of time on this. So the first thing that I implemented this and then tried this, and what immediately went wrong is that the send message system call will reject all my calls and then say message is too long. And then I have no idea what that means. So it turns out, because I designed it in such a way, because we only take the super packet and then we segment them and then we assemble it into one. The extra headers, we need to account for the size of the headers. If you don't account for it, the end result will exceed 64 kilobytes and will just explode because the kernel doesn't like that. So you need to do that first. And then, because virtual I/O net header, so the thing that accepts checksum and offloads and things, it is a very heavy contract. Once you enable it, you cannot turn it off. If you enable it for GSO, one direction, the send direction, the receive direction, you have to also account for it. Even if you don't do any segmentation yourself, you still need to prepend the header correctly, even if it's all 0 bytes. If not, then the kernel will read that and read the TCP IP headers and assume that it was the virtual net header of the contract, and then just start going mayhem. So this is a very confusing part, but I mostly borrow close intelligence to solve this, let's say. Next part is you will be, at some point, you will be able to want to verify if you are doing it correctly. So in this case, I would suggest using strace, because every time you do a send message or write or read on the TUN device, you will actually generate a system call. And strace, precisely the function of strace is to capture those system calls and the payload that comes along with the syscall. So you can actually verify what it received and what it sent out is correct just by that. You just need to add some special headers into the thing, and it should just work. It should match up perfectly. And because now that we have to handle all the checksum in software, it's very easy to get it wrong. And for this, I would recommend using Wireshark, because it will immediately tell you, it will throw a big red error whenever you see a bad checksum. So that is very useful. And if you want to do performance stuff to see if your thing is actually working as intended, then you can use PerfRecord. Finally, if you really want to get into deep, good stuff, then you can use BPF trace. So kernel actually has a very complicated subsystem, eBPF. That's another topic of its whole, but it can get into syscall pretty deeply. So that's something to think about if you are doing that. So what results I've been getting is promising. So on an Amazon instance, I was able to improve the performance of a net aggregated clients to server performance from 4 gigabytes to 5.86 gigabytes. So that's like a 50% increase. And on just a random dev machine, a ThinkPack, I can actually increase 2.7 gigabytes to 5.1 gigabytes per second. So that's like a 80% increase. But most importantly, how I verify that the TSO part is, the GSO part is actually working is by looking at the TUN reads. Because the binary has to read things from the TUN device and then send it out on the UDP socket. You can see that previously when the offload is off, it will do 3 million calls. But now it just does 100K. So that's like, so you can clearly see that it's reading multiple segments at once. and then saving all these syscalls for other use. You can also see the weight distribution ranged from 1 to 2 kilobytes, also exactly within the MTU, to 64 kilobytes of read. So that's from BPF trace. You can also see, I can also see that on the Amazon instance, if the offload is off, then it actually spends a lot of time in the spin lock for some reason. But when the offload is on, the spin locks are almost entirely gone. So that's a good thing, I think. So there is some future to do really crazy plans. If the graph looks crazy, but I promise it's not that crazy. It's basically asking kernel to do multi-queue load balancing. So people think that load balancing is difficult, but actually it's not that difficult if you can just ask the kernel to do it for you. So on the TUN device, you can actually ask it to enable this ability called multi-queue, and then you can, instead of just one queue, you actually get multiple that you can delegate it to different threads of your library. So the kernel essentially done load balancing for free. So, and how you interact with this interface is deliberately simple also. You just need a eBPF program, that's all. So you can do this on the TUN device, and also you can do this on UDP device, on a UDP socket, yes. But on the UDP socket, you need to enable the SO reuse port thing. So yeah, so you can have multiple workers to do all these things for you. So you don't have to worry about, like, for example, Tokyo threads management, for example. And I think that's a wrap. Yep. I think that's all. I will invite any questions if you guys have any. If not, then I guess that's all. Thank you for listening. What was the album? Right. I guess I can put back to that slide. So we actually do have like a lot of acceleration tools in house also, but I decided to do this on an unoptimized to see how far GSO can push the result. So the results, I think the results are pretty promising. It pushed from 4 to around 6, which is like 50%, and then 80% on my dev machine, which is, yeah. Seeing big numbers is always good, feels good for the developer. But I would say the whole work is still very much a work in progress. So in order to push this onto production machines, I think we still need to do some real-wire testing, like with public benchmark speed tests, for example, and maybe some YouTube Netflix streams to see if the results really holds up in the real world. So that will be what I'll be working towards. If you check the Lightway repo, you can also see my PR. So that's the good thing about open source, is that everything is you can read, right? Even the discussions, spicy. But that's that. Oh yeah. This in virtual. This in a virtual namespace. Yeah. So this is all just stressing out the CPU basically. It's not really, but on the AWS machine, we are actually using the network card. But I think the network card itself is also virtualized by AWS. So, yeah. 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 I think that's all. Thank you very much.